We're going to be talking about three-dimensional geometry. In my opinion, this is one of the easier sections we do in second semester. Typically, the mathematics we're doing here are not super complicated. Basically, you're doing right triangle trigonometry or filling stuff into formulas, which is like usually pretty easy stuff. The most difficult piece of this is it at times does require a little bit of like three-dimensional imagination to kind of picture what's going on. But with a little bit of practice, that's usually not too big of a stumbling block. So the first section we're going to talk about today is mostly just going to be a vocab and formula review of things that you've kind of discussed at one point in your geometry course. Now, I know that was a long time ago, which is why we're reviewing it right now. So if we take a look at these first four figures here, the one on the farthest left you would call what? Cube. Yep. Okay, great. How about the second one? Rectangular prism or rectangular solid would both be appropriate. When we say a prism, what are we really talking about here? That's kind of a generic term. So it's a three-dimensional figure that has two bases that are parallel and congruent. So basically, if I take any cross-section that's parallel to those bases and I chop there, the cross-sectional area will be the same as the base. So like if I cut that candy bar in half and I look at it, the end that I cut off is the same as the base, right? Okay. What's this next guy? Pyramid. Could we be any more specific there? We'd say that's a square pyramid. Typically, we name pyramids by the shape of their base. Right, that pyramid could have a triangular base or a pentagonal base or a dodecagonal base. Here it's a square base. You wouldn't really see a dodecagonal base, but I'm just saying hypothetically you could have one. Yeah, that would be one heck of a pyramid, right? The last figure here on this first row is looks like a doorstop, right? That is a triangular prism. Very good. Again, you hopefully can see the two parallel bases here are triangular in shape. All the other faces on the figure are rectangular, though. That's a trademark of prisms as well. Aside from the bases of the figure, all the other faces are rectangular in shape. Okay. Move on. We'll take a look at some more of these. What do we see here? The first dot on the left is a cylinder. As an aside, a cylinder could also be considered a prism, where the bases there are circles. Since, again, you chop it and the cross-sectional area is still going to be a circle. How about the second figure there? It's kind of a trick question. What?
Rectangular prism?
Yeah, it's still a rectangular prism. Yep. And if I look at the third one, what is that? Still another rectangular prism, right? Notice that the shape, the base there is a rectangle. You can see the little tiny right angle mark on there, even though it's drawn with some perspective, that it's not like a rhombus or something down there. That's still a rectangle. We should have some way of describing the difference between a rectangular prism or any one of these three-dimensional solids that goes straight up and down and one that's kind of leaning. So when it goes straight up and down and the faces are perpendicular to the base, we'll call that a right rectangular prism, and one like this one where that angle or the face is not perpendicular to the base. We'll call that one an oblique.
What's the first one?
I wrote it, right? An oblique. Everybody cool with that? So again, just another name or part of a name to be more specific about what you really mean. For the most part, we're going to be working with right figures. So if I take a look at this fourth figure here, could you be a little bit more specific? Right. Rectangle or triangular prism.
Is it oblique?
This one would also be right, though. Yeah. Okay. Everybody feel okay on naming these things? Okay. So this guy here, what do we call this? As specific as you can. This is still right. But Mr. Kulik, the faces aren't perpendicular to the base. What is, when we say it's right, what are we really looking at? We're looking at whether the height is perpendicular to the base in a pyramid. Okay, so that's why it's right. And as a separate piece of vocab, the point of the pyramid has a special name. It's called the apex. Okay. Everybody so far so good? Again, we're just kind of burning through some vocab. Next four figures here. What do we see on the left? Sphere. Okay. How about the next one? Hemisphere. Yeah, way to go, global politics. Okay. The next guy? Cylinder. And the last one? Cone. And again, on a cone, the point of the cone is the apex, just like the pyramid. So far, so good. Just some vocab. A lot of this vocab you should recognize from your geometry course, and a little bit of it might be newer, like, oh, maybe I knew that, but I don't remember if I did. But it's just vocab. How well do you have to know the vocab? I'm not going to like quiz you on it, but it would be like in part of a story problem if I say like, hey, we have a rectangular prism, blah, blah, blah. You should at least know like what it looks like enough to be able to draw a picture, you know, to sketch a picture for your work or whatever. You know what I mean? It's not like hypercritical that you're able to, we're not doing a vocab test on this stuff. Okay, let's do some area volume type reviews here. So start with the area of a triangle. One formula we know is 1/2 base times height. What's another one? How about 1/2 AB sine C? Does that look familiar?
No.
Chapter 7? Don't say no. How about a third one? Yeah, the S one. So that was the square root of S times S minus A times S minus B times S minus C, where S is the semi-perimeter. When is the 1/2 AB, or I'm sorry, when is the 1/2 base times height the most useful? What kind of triangle? for right triangles because the base and height are just legs of the triangle. When are the other two more useful? When you have a non-right triangle. Yep. Okay. How about the area of a parallelogram? Does anybody remember that formula? We'll call it base times height. Yeah. What's the little tricky thing you might have to remember about the parallelogram? The height is not a side length. Well, not necessarily a side length. I guess if your parallelogram is a rectangle or a square or something, it would be, but everybody's cool with that? Okay, here's a tough one. Area of a trapezoid. Times height. Yep. I think of it as the average of the two bases times the height. So remember, in a trapezoid, you have exactly two parallel sides. Those are the bases. And then the height is, again, not necessarily a side length. It could be, but probably not. Is that all kind of ringing some bells? Again, these are things that, do I expect you to have these things all memorized and ready to go? No. Should you recognize it when you see it and be able to use it once you have the formula? Yeah. How about circumference of a circle? 2 pi r. Or you could call it pi d, where d is the diameter. That's fine too. Area of the circle. Pi r squared. Okay. How about the area of the curved surface for a cone? So when you have a cone, the base, the circle, is actually a flat surface, right? The ice cream cone part that you'd hold, that part's all curved. Does anybody remember that area? That's pi RL, where L is the slant height of the cone. So if we look at the triangle BDC, the slant height is that side BC. Everybody's cool with that definition? Notice that I'm using a script L for slant height. Why aren't I using like just a print L? Looks like a 1. That's a Mr. Kulik mistake. Is your L turned into a 1 and you screwed up your answer. I'm going to try to outsmart myself and use a script L there whenever possible. Everybody okay with that? How about the volume of a cone? Do you remember that one? It's 1/3 area of the base times the height. So I'm going to use the capital B for area of a base versus a lowercase b that we'll use as like a side length that we're calling the base. Everybody's okay? And specifically in a cone, the area of the base is always a circle. So you could also have said 1/3 pi r squared h. That's okay as well. Oh boy. There it goes. I don't know why that seems to do it, but that always seems to solve the problem. Okay, let's say we want the area of the curved surface of a cylinder. So your cylinder, the bottom and the top are circles. Those are flat surfaces though, right? The side is the curved surface. What's that area for the curved surface going to be? The circumference of the circle times the height, or just 2 pi RH. How about the volume for a cylinder? just area of the base times the height, right? And since a cylinder, the bases are always circles, we could say that's pi r squared h. So far, so good? Everybody happy still? Volume of a sphere. This is maybe a tough one to remember. How about 4/3 pi r cubed? I think in your geometry class, did you guys derive that formula in there? It's a tricky one to derive. No? That's okay. If you take AP Calculus, I'm almost certain that whoever teaches that course would derive that formula using integrations with a solid of revolution, which is kind of like a little bit overkill to do it, but it's kind of neat. How about the surface area for a sphere? Anybody remember this one? It's 4 circles. Weird. Also kind of a tricky derivation. If you tried to derive that in your geometry course, you may have or you may not have. How about the volume of a pyramid? It's the same as the volume formula for a cone, except what's different? Yeah, that area of the base, the shape for your base, could be lots of different things in a pyramid. So we're going to leave it as capital B. Now, if it's a square, you know, length times width or whatever, fine. Or a rectangle, fine. But if it's like a pentagon, like, ooh, boysy, can be kind of tricky there. So the volume of a prism in general. Area of the base times the height. If you're talking about a rectangular prism, the base is a rectangle, so length times width would be the area of your base, and then you have times height. Whereas that's the familiar box formula that we probably remember from geometry, length times width times height. I usually think about it as area of base times height, though, because it's a little bit more general, since we'll definitely see prisms that aren't rectangular prisms. Okay. Now, at this point, you're probably thinking like, oh, Mr. Gulick, that's so many formulas. If you took a look at the review for this chapter already posted and you scroll to the end to look at the formulas page, it's the same formulas page you'll get for the exam. It looks like probably everything we just talked about here is on it. So I think you'll be okay without having to memorize a whole lot past like how to use some stuff. So I don't freak out about like, oh my gosh, I'm going to have to make flashcards. I try really hard not to make the course like a flashcard course, right? Yuckers. All right. The remaining sections of this chapter I'm going to do via PowerPoint because it involves kind of a lot of drawing, and you've seen Mr. Kulik's drawing skills and they are less than optimal. The 3 PowerPoints that I've made for this chapter on our My Notre Dame page in the download section here, along with all like the archived agendas or whatever. So if you want to go look at any of these PowerPoints, feel free. If you're somebody that likes to take the notes by hand, I might recommend against doing such a great job on these because doing all the drawings is kind of a hassle. But that's the plan here for the remainder. We're going to do 9-2 today, then we'll do 9-3 and 9-4 next time. So in section 9.2, we're going to be talking about finding the lengths of segments within a 3-dimensional solid. So to do this, we're going to be relying on what we're going to refer to as calculation triangles. So that's going to be a right triangle that's kind of inside of that 3-dimensional figure somewhere. So for example, if I have the right pyramid as shown here, one example of a possible calculation triangle would be this triangle ABC. Everybody's okay with that? Or is there more calculation triangles than this, just this one? Of course, yeah, there's going to be lots of them. Sometimes the trickiest part is like finding the one that really makes the problem easiest. Okay. We're going to take some time here and just kind of buzz through some examples of more calculation triangles, some of them being ones that are maybe not obvious at first sight, to just help build out a little intuition for looking at these three-dimensional objects and kind of finding these things. Okay with that plan? Okay. So if I look at this cuboid here, oh, that's another generic term for rectangular prism. I think that's more used in Europe, but I see it pop up here and there. If you're going to take the IB course, I think they love the term cuboid for whatever reason. Yeah, it's a lot of Europe. Anyways, the pink calculation triangle here is very obvious. That's a right triangle. Everybody agree? The blue triangle is also a right triangle. Good. It doesn't look like it, Mr. Kulik. Well, you're taking a three-dimensional object and embedding it into a two-dimensional space like a sheet of paper or the projection screen. So there's some distortion that happens. You're familiar with this. If you look at your maps in your history class, you look at Greenland, looks gigantic, like it's the same size as South America, and it's nowhere near the same landmass as South America. Again, that's a result of distortion from projecting a three-dimensional object into a two-dimensional space. There's actually a couple different ways you can project the globe into a map. I think the one you're most often see is like the Mercator Projection, which kind of distorts the size of the things in the northern hemisphere, like Europe and stuff. Probably an artifact of Eurocentrism that became the most popular map projection. But why is North America and Europe on the northern hemisphere? Why is that on top? There's no real reason. You can put South America on top if you wanted to. Just, again, elitism. Anyways, back to this. Yeah, it was a good one, though. Anybody watch The West Wing? That's a TV show about the president? Yeah, you watched it? Okay. So there's an episode where they talk about like these different map projections on it. It's my favorite episode because it's so stupid and strange, but like also really interesting. Like, oh, this is neat. Anyways, the blue triangle here is a right triangle. The right angle is this angle G. How do I know that's a right angle? It's because I know that the sides or the faces of my rectangular solid meet at a right angle. So the segment FG in one side, the back side here, and the segment GD on the end have to meet at a right angle because those two planes that they're in meet at right angles. Everybody can kind of see that. Tough to see initially when you draw that. You look at it and you're like, that doesn't look like a right angle or right triangle. It is. G's the right angle. Okay, so we're going to do a bunch of these unexpected ones where I'm going to show you some triangles in here that's like, that don't look like a right triangle when you draw it on a sheet of paper, but you have to think about it in 3 dimensions. And okay. All right, we'll do another. So here, again, the pink one, EFC, pretty obvious that should be a right triangle. It's half of a rectangle, right? BGE is also a right triangle. Angle B is the right angle. Again, for the same reason, we know that because this is a right triangular prism, that this edge should intersect the base at a right angle. Okay. Look at another one. So here, the blue triangle is the obvious one. We actually looked at this as our first example of a calculation triangle, this specific one. Easy to see that's a right angle, or at angle F. The pink triangle is also a right triangle, and you're like, Mr. Kulik, that's clearly an obtuse triangle. It looks so obtuse. It's just distorted, man. Remember that because it's a right pyramid, the height is intersecting the base at a right angle. So any segment in the plane of the base is intersecting the height at a right angle. Angle F is a right angle there. Woof. It's okay. You'll get used to it. It just takes a little bit of practice. That's why we're doing these, is to like help you see it, right? Sometimes it helps to just close your eyes and imagine it, looking at it from like a three-dimensional perspective in your head. If you imagine, it's like, okay, yep. When you look at it in the real, like, it's like, oh, this is just a flagpole coming into the ground. So any segment that I'm drawing, like, makes a right triangle. It's like, okay, yeah, sure, I guess. Keep going. Okay. Now we're into some specific calculation examples. Okay. For any of these kind of story problems, my general plan is going to be to sketch a picture. Typically, if it's a three-dimensional solids picture, we'll provide you a picture, but not always. Identify the calculation triangles that are going to be relevant given the information, and then sketch and label those calculation triangles. I like to draw the right triangle off to the side with the measurements on it, so I'm not like cluttering up my three-dimensional picture, because you might have 2 or 3 triangles going on in there with different measurements all over the place. It gets a little messy. And then solve the triangles to get the relevant information. Okay. So in our question, we have a shoebox is 32 centimeters long, 18 centimeters wide, 11 centimeters high. You want to calculate the length of the longest rod that would fit inside the box. So we have a box. You want to fit the longest stick possible in there. How's that stick going to sit? Yeah, diagonal going from like the upper top to the lower bottom. Yep. So here's my box. And our rod here would go from like G to A. So the calculation triangle involving that segment GA would be this GAC, where C is the right angle. Everybody see that? So I just want to find a right triangle that involves the segment that I'm interested in. Now GC, I know that's the height of the, same as the height of the box. That's 11 centimeters. AC, though, I don't know. I would need to find AC in order to find AG first, because I only know one measurement inside that right triangle. Does everybody see that? So I'm going to look for a second calculation triangle that involves the side AC and 2 measurements that I do know. Anybody see a triangle that does that?
CDA.
Yeah, CDA here, right here in the front, on the bottom. So I can solve that using the Pythagorean Theorem. And I get that the segment AC is the square root of 1348, which is like, I don't know, like 33 something, 34 something. But that's what we needed in order to solve for AG, right? Oh, 36 something. So that's the square root of 1348. It just was easier to make it a decimal to get it onto the picture than to put the square root symbol in there. It was turning into a hassle, and I quit and just made it a decimal. But now I can just, again, do the Pythagorean theorem to find AG, which is what I'm really after. Oops. So notice I used the square root 1348 on there because, well, I'm squaring it. So it just blows up and it's really easy to deal with. So I get AG is the square root of 1469 or 3833. So that's an example what you might have to do. Not terribly complicated. It's all right triangle trig. The hardest part was like getting the measurements in the right places and figuring out what triangles you needed. So the setup was really by far the hardest part. The actual algebra is like, you know, that's like algebra 1 algebra where we're just using the Pythagorean theorem, Holmes. You're right. Let's do another example. So this one's got a little bit more involved. It says that EABCD is a square-based right pyramid with sides 12 centimeters. So it's talking about the sides of the square base are 12 centimeters. And the height of the pyramid is 9.5 centimeters. We're going to calculate the height or the length of EC. So here's my square-based pyramid. The apex is E here. I'm looking for EC. So the calculation triangle I drew was EFC. So I have EF already. That's the height of the pyramid. That's 9.5. I'm looking for EC, but I don't yet have FC. So I'm going to need to create a second calculation triangle to find FC. Does anybody see a good one to use there? Yeah, there's actually two that I think would be reasonable to use here. So you could do CFD, that's a right triangle. Although that's a little tricky to know why that's a right triangle. Does anybody know why? Since the base is a square, I know that the bisectors of a square meet at a right angle. So FD and FC have to be perpendicular to one another. And since this is a square is also a parallelogram, I know those bisectors or those diagonals bisect one another. So these are actually the same length, FC and FD. So I can do a Pythagorean theorem and solve that because they're both x's. You could do that. What I would do, though, is ACD. Because I know that FC has to be half of AC. Again, because the bisectors of a parallelogram bisect each other. So I did this. And that gives me the length of AC. And I know FC is just half of it. Is everybody okay there? So I have to recall a little bit of geometry knowledge to justify that to myself. But the nice thing about those geometry theorems is it looks like what it is, right? Like if you draw the diagonals for a square, they look like they're perpendicular. They are, like they look like they bisect each other. They do, I'm never going to ask you to cite a theorem, but I'm going to cite them when I use them because it's good review and it's rigorous. You know what I mean? That's my expectation for myself, not my expectation for you. Fair? Yeah, I think so too. Okay, so we have FC now. Really what we're after for this question was EC. So when I do that, I get 12.74. Just again, using the Pythagorean theorem over and over and over again right here. Pretty straightforward. The next part of this question says that M is marked halfway along one side of the base. So there I've marked M. It wants me to calculate the length of EM. So the calculation triangle I've built this time is EFM. Everybody's cool with that? And I know EF is the height, so that's 9.5. I have that already. What's the length of FM? Good, 6. Since the side is 12, I know that, and I know F is like the absolute middle of my square. So like this side that's obviously parallel and equal to AD, F is in the middle of. So everybody's cool with that reasoning? Okay, and then I Pythagorean theorem again, and I get 1124. So I noticed that EM was shorter than EC. Everybody agree with that? My last question is explain why. I think the best explanation is if I take the triangle EMC, that's a right triangle, correct? In that right triangle, M is the right angle, so EC is the hypotenuse, which better believe has to be longer than the leg EM. Cannot possibly be equal. I think is probably your best explanation. When I wrote this PowerPoint, I think it was me that wrote this PowerPoint. I didn't use that explanation. I just said like, oh, one is the slant edge and one is like the height of a face. So they're just like different measurements, period. That explanation I just gave to you I think is better, but this is fine too. Everybody's okay with that? One more example and we're going to be done for the day. Woohoo!
That's a first.
Yeah, I know, right? All right, we got this cone. We're told AB is 11.3 and the apex angle, ABC, is 53 degrees. This is an alternative notation for drawing an angle as you put this little angle symbol on top of the three letters. Whatever. I think, again, popular in Europe. Calculate the radius of the cone. So we're looking for DC. So the calculation triangle I drew was this BDC here because it involves the radius. Everybody cool? So obviously this side is 11.3. What else can I get out of this? That's not enough, right? That's only one measurement. Yeah, what is that angle? Okay, so why can I just divide 53 in half? It needs a little bit more than that. So what's special about the triangle ABC? What do we call that kind of a triangle, though? Doesn't that triangle have a special name? Isosceles, yeah. Since this is an isosceles triangle, the two side lengths are the same. We know that if I take the apex and we draw a height, an altitude, I think is the term we used in geometry, that altitude is also going to be an angle bisector. And it's also going to bisect the other side. So that's special for isosceles triangles. I think we had a test question in chapter 7 where I gave you a story problem with a flagpole in between two people that wasn't an isosceles triangle, and everybody tried to like bisect the side or whatever down here. Does that ring a bell? Yeah, or I shouldn't say everybody, but many of us tried to do that. And probably was everybody's first instinct before you thought about it a little bit more. But yeah, so here's the takeaway though. If in a cone, is that always going to be an isosceles triangle? In a right cone, it'll always be an isosceles triangle. If it's oblique though, you lose that possibility. So you do need to be a little bit careful about that. But yes, what Aiden says is true here. I just wanted to make sure we justified it so that like we were using that property correctly, particularly since there was a test question a while back that like some of us whiffed on it a little bit. I just wanted to make sure that we came back and talked about it a little bit more as to when that altitude is also going to be an angle bisector or a side bisector. And you need an isosceles triangle for that to happen. Okay. From here, though, now we have two measurements inside a right triangle. What are we going to have to use in this case? SOHCAHTOA. Well, which one do we want? Sine. And it's easy. That's it. That's my PowerPoint for section 2. At this point, you guys should be able to finish 1 through 7. Next time, we're going to finish up the chapter. We're going to do sections 3 and 4. What do you suppose Mr. Kulik's going to want to do before we leave for break? Homework quiz. What should you definitely want to make sure you've done before next time? 1 through 7, because that's what the homework quiz is going to be based from. But it's only 7 questions, guys. It's not so bad.
Does each one of them have 6 parts?
No, not 6 parts. Not each of them. No, I think a couple of them have like 2 or 3, but most of them just have like 1 part. It's not so bad. Okay.